if you define as 0 and 1, then basically 0 means first value, and whatever value you get, the parameter b1 would be the difference between the two alternatives. So better is to do this way, and the difference between the two is then 2bj. So basically bj here is the b1 parameters. Now let's see. So here for 3 categories, you don't want to use 1, 2, 3. What you want to do is define x1 and x2. All right. So x1 is 0 means not type A, and 1 means type A. x2 means 1 is type B, 0 means not type B, and then you have 4 possibilities actually. So here you have 0, 0 is type C, 0, 1 is type B, and 0, 1, 0 is type A. Basically, so you have these 3 possibilities. But if it is 0 here, we define 0 as not type A and 0 as not type B. So basically, if it is not type A, not type B, so it is type C. And when you will do the regression, we'll come up with the parameters B0, B1, B2, and error. So B1 now indicates whether it is A or not A, and B2 indicates this is B or not B, right? So this is the difference. So somehow it gives some idea of B, and this gives some idea of A, and then to get the idea of C, you have to combine both of them. All right, and the way you will do it, by A equal to whatever, and then by B equal to, you put 0, 1, and by C equal to, put 0, 0. So yc equal to will come out b0, and ya will come out b0 plus b1, and yb will come out b0 plus b2. So basically this is the effect of C, this is the effect of A, and then this is the effect of B. But the way we have defined is like this. We have defined that C means when x1 and x2 are 0, 0. So when you put 0, 0 here, x1 and x2, then yc equal to b0 plus error. Type C is a predictor. Type D is a predictor. It's just how you code them here. These are the predictors. This is actually, there is only one predictor variable which has three types. So the x is represented by 0, 0. That's the whole new thing that I'm trying to put here, is that normally before this you would have just thought about 1, 2, and 3. X equal to 1 is this, x equal to 2 is this, x equal to 3 is this. And there's a problem with that model, is that you are somehow assuming that they are in this order, and they're not ordered variables. Right? So you cannot have numerical values that indicate some order. So the way we took here is 1, 0, 0, 1, 1, 0, 0, they don't indicate any order. No, see, the thing is, yeah, this doesn't order. If you combine those two, like you said, this is 0, this is 1, this is 2. But we are clearly going to see, it could be in any order. Actually, you can work it out that if, let's say, they are ordered such that A is short, B is medium, and C is long, the parameters will come out still correctly without any effect. Anyway, so what I wanted to say was, and this you can continue for so let's see, for 3 variables, we did 2 predictor variables, right? For k variables, you will need k minus 1 predictor variables, okay? Not log k, not log base, log 2k or something like that. It's k minus 1. So basically that's why it is not ordered. When you have k minus 1 predictors, first one says it is A, B, C, D, E, F, G, and the last one is, if none of those, then this is it. Right? So you're not using all possible values here. You're just using 0, 0, 0, 0. With 2, we don't see that very much, but there are 4 possibilities, and we're using 3 of them, and it looks like we're just using almost everything. But with k, you have 2 raised to k possibilities. You are using only k possibilities out of those. With actually k minus 1 variables, you have 2 raised to k minus 1 possibilities. You are using only k out of those. All right, is this last point clear to everybody? So let's say if you want to do something which has 4 categories. How many predictors do you need? 3, okay. And you will define them as x1 equal to x1 is equal to 1, 0, 0 is A, and B would be x1 is equal to 0, 1, 0, and C is equal to 0, 0, 1, and D equal to all zeros. Good. So that's how we define it. And then you can get the average values as we said. By putting the values, you know that this is the YA bar, YBC bar, and then you can get the effects. So this is what we already said, that for k variables, you need k minus 1 binary variables. So generally, that alternative that you want to select for this last one is better than if it is the status quo. That is something that is a standard that everybody wants to compare against. So that you put as 0, 0, 0, 0. And then everything else comes out as increment over that. Right? Because as you notice that B0 was the standard, and everybody else we measured as B0 plus B1, B0 plus B2, B0 plus B3. So B1, B2, B3 are the increment over the standard. All right, so let's now do Unix versus Argus as a categorical variable. You have done this, I think, as a homework. So now the problem here is very simple. There are 2 operating systems, Unix and Argus, and they are trying to send some data bytes and measuring the time. And so this is the size of the packet, and this is the time. And now we going to have the second variable. The first variable is the size. So this is the first variable, which is continuous. All right. The second variable is the operating system, and it is categorical. So we are going to mix and match now, right? X1 is continuous and X2 is categorical. Hold on, they put 0 and 1. All right. Now, so they did, I mean, this is a case study done by some students anyway. Later on, as we will see, I would have preferred -1 plus 1, as I indicated before. But this is the result that they put, 0 and 1. With 0 and 1, we get B0, B1, B2, and all 3 parameters are significant because they do not include 0. And the regression explains 76.5% of the variation. So this is R squared. Per byte processing for the both operating system is 0.025 millisecond. That is the integration, that is the B0. If you have 0 and 1, when you put a 0, per byte is B1 anyway. B1 is always, okay, so B1 is what we are reading here. So B1 is the per byte cost, 0.025 is the per byte cost. The setup cost on 2 operating systems, Argus and Unix. So if you put 0, you get Argus, and the setup cost, and in that case, it is B0 plus B1. And then if you put 1, then you get Unix, and that is B0, B1 plus B2. So the B2 actually is the Unix Argus difference. So minus 14.927 is the difference between Argus and Unix. Now, to find out how much it is in Argus, you have to just put a 1, and then that means add up all of these. On Argus, you will just put a 0 here, so you will add up these 2. So on Argus, it is 36.73, sum of these 2. And on Unix, sum of all those, and that comes out to 14. Well, I haven't given the number. All I'm saying is 14.927 millisecond more than that with Unix. So Argus is more. So basically Unix is basically that number, whatever comes out, 22 something or 21 something. before I move, I mean, is it clear how we interpret these parameters then? B0, B1, and B2. Depending upon how we select this coding, we have to put that coding and find out Y Unix and Y Argus. Y sub Unix equal to B0 plus B1 plus B2. Y sub Argus equal to B0 plus B1. Done. Right? If you want to know the difference between the two, then you have to subtract those two. If you want the average between the two, you have to take the average between the two. Now, in 14.1 concluded there was no significant difference in the setup cost. The per byte costs were different. And 14.1 concluded per byte cost is the same, but the setup costs are different. Now this is this is a mathematical trouble, is that the conclusion that we did before by putting two different separate regressions is different than here. And this is the statistical technique applied without understanding system can lead to misleading results. And so that's what happened here, is that you really need people who know the system before you can do the correct modeling and the correct interpretation of this. And the assumptions are different. In 14.1, we assumed that the processing as the setup costs are different, and therefore there are 4 parameters. And here we have only 3 parameters. And so the data showed that the setup costs were numerically undistinguishable that time. Here, we assume that there is a common setup cost, B0, and therefore we can mix the two just to find out the per byte cost. So in the second model that we did, somehow we assumed that the setup costs on the two operating systems are same. That's what we assumed. We didn't realize it by putting it this way. But B0 is common for both of them. The only thing we are modeling is the per byte cost. All right? But if the setup cost is different, then you cannot use this model. Everybody understands what is setup cost and what is per byte cost? When you have B0 plus B1 times X1 is the size of the packet. So that is per byte cost. B1 is the per byte cost. So, hold on. Actually, I said something wrong, which I should correct myself. So, we are using, this is B1 is the per byte cost. And we are assuming that this is the same for both operating systems. Because we are only distinguishing this part, which adds up to B0. B1 is constant. B1 applies to both. Then we say, when we said 0.25, that is B1 per byte, that is not for one operating system. That is for both operating systems. We are assuming that both operating systems take the same time for per byte, which is an assumption we made, but that is not true. That may not be true. If it is not true, then you need two different B1s. Right? And that means you need two different models then, basically. Let me write down the model. The total, okay, let's write down this way. I mean, you can do it right here on the screen. So if we were just not worrying about Argus, then the model is B0 plus B2 plus B1 X1 for Unix. B0 plus B2 plus B1 X1. B0 plus B2 is the setup cost, and B1 is the per byte cost for Unix. Right? And then if we were just doing for Argus, then the model would be B0 is the setup cost and B1 is the per byte cost. Right? So we are assuming for both cases the same per byte cost. The setup cost is different. And so we are assuming different setup cost but the same per byte cost, and that is this model. The previous model was both of them are different. The setup is different and the per byte is different. Oh, because see, setup cost is 0 byte. You just put x1 equal to 0. x1 is the packet size, right?
But I can also say x2 equals 0.
Well, x2 is defining the type. I mean, it doesn't define the size. Okay, so there is some fine point here that you have to understand, is that when you put many variables in a model, you have to understand what you're doing, how those variables, how they are changing the model. The model used in case study 15.5 is assumption that the per byte cost is same. And that could be the case if it is related to something else like disk or operating system or network or something like that. But the thing is, the only people who will know this is the programmers. It's very difficult for a statistician to look at the data and say, well, what is the case? All a statistician can do is probably analyze both ways if they understand that they are making this assumption, and then see if they get into this kind of thing. Okay. So again, we came up with a case where simpler models are better models. Study was based on the assumption that the processing as the assessor sign are different. So we are assuming the same per byte cost. And that's what in the next line is. This one is the cost. This is the line. So here the point is that if you know that the per byte costs are same, because this has nothing to do with the two things that we are talking about, then this is a good model. All right, that finishes categorical variables. Now we go into another complication, and that is if it is not linear. If it is not linear, then is there a way to make it linear? If it can be made linear, then we call it curvilinear. So not everything is curvilinear, and there are very different non-linear solutions, but let's go one step at a time. Let's assume what can we do with the curvilinear. For curvilinear, basically we do whatever is required to make it linear. So for example, if y equal to b x raised to a is the thing that we see that it's like parabolic or cubic or something like that, then we take the log on both sides and it becomes linear. Now we predict log y as a function of log x. Now they're linearly related then. So here are some examples. If y is equal to a plus bx, the linear would be y is equal to a plus b times 1 upon x. 1 upon x is the transformation that we use. If y equal to 1 upon a plus bx, then the transformation is 1 upon y is equal to a plus bx. This is a linear regression. And so on. If a predictor variable appears in more than one transformed predictor variable. So right now we had kind of life simple here. In most cases, the predictor variables were one variable like x raised to n rather than x1, x2 or something like that. If you get into those issues, then you will certainly get into multicollinearity, because now you have two predictors which are clearly correlated because they are a function of the same thing. Different functions of the same thing. And then you have to find the subset that gives the best regression with the minimum number of parameters. Here is an example of curvilinear regression. Amdahl's law. So Amdahl is another company and they wrote their own law, and their law has to do with the I/O. And the law says that I/O rate is proportional to the processor speed. If you get your processor becomes 18 months twice as fast, then you need I/O which is twice as fast. Actually, we have been lagging behind on that one. I don't know whether it is still true, but the disks have not become as fast as you would want them to be. CPUs have become very, very fast. Right? So, but anyway, this law doesn't say that they have to go. But basically, at any given time, maybe if you find processors which are systems which have high processor speed, they will have high I/O rate. So somebody did this measurement. This is the MIPS rating of the system. This is the I/O rate. MIPS rating the system. And before we accept the proportionality, let's assume that it is not proportional, it is power of something. So we assume that the I/O rate is alpha times MIPS rate raised to B1. If you take a log of both sides, you get log I/O is equal to log alpha plus B1 times log MIPS. It's quite possible that, so here this is B0 and this is B1. Now, so let's just do that. So this is the X. So this is the log. These are the log values. x1, y, observation number, and we do the b0 and b1. This is the mean, this is standard deviation, this is the confidence interval. So none of these are 0. That's good. Now both coefficients are significant at 90%. Regression explains 84% of the variation, which is okay. I mean, can't complain too much. At this confidence level, we can accept the hypothesis that the relationship is linear since the B1 includes 1. The question is B1 1 possible? If B1 is 1, then it is a linear relationship, right? And since B1's confidence interval includes 1, we cannot reject, we cannot say whether it is not 1.
Why does it measure if it includes 1 or not?
Oh, because Amdahl's law says it is proportional, directly proportional. So Amdahl's law says B1 equal to 1. It doesn't say it is proportional to a square or 1.5 power or something. It says proportional. Okay, so you saw actually one use here. One thing is that we learned about curvilinear regression, but we also basically learned how to interpret these confidence intervals. We already know that. We use it for zeros all the time, but now we see that we need to check it for 1. Then we verify like before. We do the test. So one thing you would do is, there are 4 tests. First you check for the linearity. Then you check for the randomness of the errors. Then you check for the normality of the errors. So this is the last one, normality of the errors. QQ plot. Normal quantile versus residual quantile. And this looks pretty straight line. Going further from curvilinear to other transformations. So other transformations are that, and it could be any general transformation. So here we have square root of y. And the reason you need to go for transformation is, if it is a physical consideration, then it is the best. Is that you know the system, you know that in this system this is square root or a square or cubic or something like that, then go ahead and try that out. That is the best reason. Rather than mathematically somebody sitting down and seeing whether it is square or cubic, systems knowledge takes precedence over statistical analysis. If you know something, then just go ahead and use it. Then another thing is that if you don't, basically you are a mathematician only, which is often the case, that, you guys are actually best suited to be performance analysts because you know the systems, you know the computer science. But sometimes what happens is the people who do the analysis, they don't know computer science, they just do analysis. So in that case, one of the very common thing that you check is y max upon y min. What is the minimum value that you have measured and what is the maximum value you have measured? What is the ratio of those two? If the ratio is large, that means the variation is large, then you may want to check for log transformation. When the variation is so large, then your one thing that you might be violating is the same variance for all residuals, and maybe log will fix that because the variance of the log and then the errors would be less. In that case, what you will see is the non-homogeneous spread. You will see a spread which is basically going up as the predictor goes up, right? And on the other hand, if you notice that the standard deviation has some function g of bi-var. So remember, one of the tests, second test was independence of the errors, and to check the independence. Basically, there is no foolproof test for independence. All we do is dependence. So what we do is we measure the errors. We plot the errors as a function of bi hat. So if you can somehow think of a function g, then if you use a transformation h, such that h is 1 upon g, integral of 1 upon gy dy, that will solve the problem. That will make the standard deviation constant. Okay, so let's take an example here. let's say we plot and we find out that the standard deviation of the errors is a linear function of y bar. It goes up linearly. So in that case, basically G is simply A times Y. Remember this formula. GY. Standard deviation is G by bar, right? So standard deviation is 1 upon A y bar, and then you take the integral, that comes out to be A log Y. So if you do A log Y, that will make the standard deviation constant. It will not be a function of y bar anymore. And these are other possibilities. Suppose you find the standard deviation is square root of y bar, then you do this. Is power alpha square, 1 minus square, this function, that function. So for each of these functions, it's all same integral formula we are using, and this is the transformation. So it's pretty good. Basically, you have to somehow guess what the standard deviation looks like, and then from there you can figure out what the solution is. Basically, people spend a lot of time. I mean, analysis, you don't do it in a day. I mean, people spend 3, 4, 5 months measuring, analyzing, simulating, but they make common mistakes. So these are the common mistakes. So for example, I have not seen anybody plotting errors as a function of predictors. I mean, we say that in the book, but not in the papers. Nobody plots that. They don't check. If they don't check, then they won't come out that their model is wrong, right? And that's the whole purpose of writing this, is that you have to first know what assumption you are making, and sometimes the assumptions are hidden, like we saw that in B1, B0 example, that the hidden assumption was there. And so you have to clearly understand what assumptions you are making, and then you have to verify those assumptions in the real life. All right, so now we finished several things. We finished the curvilinear, we finished the transformation, general nonlinear stuff.